Oh, yo, what's up, everybody? Welcome back. Today, we are trying to investigate some crashes that we've seen when we are writing some custom firmware in Zig to run on the Raspberry Pi Pico, a little microcontroller that we're using to build an Xbox controller from scratch. Right? We bought this thing and we look online and we say, how do you use it? He goes, use the Raspberry Pi Pico SDK. And we say, fuck you. No. We will not use the SDK. We're going to do it ourselves. And so that kind of ends up in this case where we have this like Zig thing that we build. We kind of package it up in a way where it can run on the firmware of this guy. His like startup sequence is kind of like he looks at some read-only memory. It launches like some bootloader. That bootloader loads our bootloader. We set up like the runtime for our application, which is kind of just like set the stack pointer in reality and like copy paste the code into like the section of memory that we want it to be in. And then we run it, right? And what we saw yesterday is that we were trying to configure USB to run on this thing. And we say, hey, system on a chip, you've got like a USB controller in you. Could you please like turn it on and could you do some stuff? And like when your stuff is ready, could you let me know about it? Right? Kind of hand wavy. We're skimming over details because that's not the important part. The important part here is that part of that code was to kind of like process like this message that came in over the bus. And you know, that message, we had a descriptor type in it. And like in here, we were trying to write something as simple as int to enum, turn this number into our thing, and if it's something that you don't understand, unknown. So here, if this code is in this block, this function just like immediately crashes. Let's see if we can bring that case back. I think it should be like if I do this, we should be able to see the problem. Right. So here we see in init USB, they call the signal handler because the USB interrupt was fired. And if we look at frame 2 here, we're like at the like function declaration of this guy, which is very confusing. And then immediately we go, fuck, something wrong. Interrupt 3. We have our interrupts all hooked up to do nothing with a breakpoint on them, right? So that's what you're seeing here. This is interrupt 3, which is defined in the ARM v6m manual as a hard fault, which they say happens basically when like some shit goes wrong, right? So I don't really understand what's happening here. Just he's saying something went like horribly wrong. We don't know how to handle it. Freak the fuck out, right? And if I just like don't do this, if I replace in here this with our copy pasted version of int to enum, right? And in him, he returns an optional instead of an error. I replace this with or else. I believe this is just like totally fucking fine, right? No crashy. So why? That's kind of the question we're trying to answer for ourselves. We've also proven, we were trying to like slim down this test case. So we kind of have another interrupt handler that we are running. It's called, we run a function called crash me. And all this guy does is he runs this assembly that calls like svc0, which is an instruction that this guy says, will trigger the sv call interrupt. And it's just like an exception caused by this thing. We're like, okay. I think that this is supposed to be used for like switching privilege modes, I think. Not really sure. I haven't really read, but it's just like an instruction we can call to trigger an interrupt, right? So we call this guy, no more USB stuff in handling or being involved. We just end up in this guy. Right here, we try to do that cast and we breakpoint, right? Simple. So what we found in happy hour is this is totally fine, right? Everyone's happy. We get to our breakpoint in the SVC handler. And we continue, and everybody's happy. However, if we initialize the USB clock and then swap the order of these, then we end up in our hard fault handler. The USB clock shouldn't be like playing a factor in this at all. The USB clock is just like sitting over there doing his own thing. It's like, what the fuck is going on, right? That is the quest for today. So that's what we're gonna be looking into. Alt F4, thank you very much for the raid. I apologize for not immediately acknowledging, but we had to finish explaining. We had to finish. Yeah, so that's what we're working on. There's not really much of a plan. This is kind of like an investigation stream, right? So it's like we're just gonna poke and prod, see where we end up, and then hopefully end up somewhere interesting. Yeah. Let's get moving. So I guess really what we want to do is understand what is happening when an error is thrown, right? Thrown is maybe a strong word here, but like, you know, you might think that an error in this language is just a like integer, right? But I think that it's not so simple because you can do things like you can in here write like error trace, right? And this will give you like a back trace of where this error was written down. So like clearly when I do this, he must be interacting with the system like in some way. He must be writing down somewhere like error happened, error, right? That's gonna go somewhere. And so my suspicion right now is that maybe in the context of an interrupt handler, that needs to go somewhere. Like hand wavy? I don't know, man. I don't know. And maybe like I wonder if this USB clock isn't even relevant as much as just like the addresses of where everything ends up, right? It could just be like it's trying to write that shit somewhere and we're not like handling that properly. Maybe. Also because like in reality, this USB init clock, like this is like a persistent thing, I think, right? So if I comment this out, like, oh sorry, I think that when I run this, I think the USB clock is still on. So like really, what is the difference in hardware? Like not really anything, as far as I understand. So like what the fuck, right? It seems more likely that it's like addresses are changing or something. We could actually look at that. Can we look at like the address of CrashMe? This is at 2000, I guess. And if we turn this back on, I assume that it's actually still at address 2000. But I guess CrashMe isn't the thing that's interesting here. I guess SVC handler is kind of the more interesting piece, which he doesn't know about. Because this guy's not an exported function, so maybe it's not easy to like look at it that way. Spooky Skeleton, thanks for the prime. Much appreciated. But maybe we could put a break. We could just look at the breakpoint that we hit in this case and see. So we hit this breakpoint. Can we look at this? Key. Disassemble maybe. So we're at like A62, right? A62. And if we turn on init USB clock, I wonder if that changes. Frame for disassemble B92. So this thing is moving, which is maybe interesting in some way. Right? Maybe that's having an effect. That's my only real reasonable lead right now. But yeah, I guess what I want to do is I want to look at like what the fuck is an error. I think that's important. So we can go into the Zig codebase and we can maybe check what revision we're on. 0.14.0, great. I don't really know the Zig codebase that well. I don't really know like where like types are defined and stuff, but surely if we grep for like error, like const error equals like maybe this is defined somewhere. That's not going to be very useful. What about like error return trace? Like somewhere implements the error return trace built in. Okay. Error return trace. So, like, what happens here? In AST generations, probably not what we're looking for. This, I guess, is like Zig intermediate representation. ZIR seems kind of like it. What about like built-in function? Okay, this is just like its way of mapping the built-in to the tag. Okay. We look for like error return trace here. Sema. I don't know what sema is. Semantic analysis of ZIR instructions. Sure. So here they go. Let's make this guy, and he's gonna say get error return trace. And what's this guy doing? What's this guy doing? He's like probably looking up where the stack trace is stored. Maybe. Not really sure like what sema is. That'd be kind of. I wonder if we can like get some information about this from somewhere. I assume that this is like some sort of. It says like something about like semantic analysis used for compiling ZIR into AIR. Be interested to like know what that means. I assume ZIR is like. I wonder if there's like docs somewhere. Doc. Langref. This is like the language reference though, not like compiler developer reference. Sema is what runs the comp time code. Interesting. Can you replace the int to enum again with a custom function that returns an error now that you have found that you can't crash without the you can crash without the USB clock? Yeah, we can do that. So you're saying like in here, in our SVC handler, I think I'm not sure that I've proven that we can crash with the USB clock. Just that the crash is more about the fact that the code to initialize the USB clock is there, not that the USB clock is on, if that makes sense. But yeah, it'd be interesting to just be like, we have a function somewhere that we wrote, do a thing. Right? Like, it would be interesting if just like any error is causing this. So like, does this cause the same thing? Just raw return an error. Yes. Yes, it is. Maybe put some other code in init USB clock. Yeah, or like replace this with like another function call. Maybe. But I wanna read through the Zig stuff first. What I really want to know is like, what is an error doing when we construct it? That's like the most interesting part to me. Which means that we have to kind of like find where we have to like kind of like understand the breakdown of how Zig's stuff ties together. So we were in Sema a second ago. This is just source Sema. I want to know what like ZIR and AIR are. So is there like ZIR Zig? Zig intermediate representation. So ASTgen converts AST nodes into untyped IR instructions. Next, Sema processes these into AIR. Is there like AIR Zig? Analyze intermediate representation. Okay. And then I assume eventually this stuff probably gets turned into like x86 assembly? Or sorry, x64 assembly? There must be like Codegen. Okay. I assume Codegen is the part that like actually does the exporting of like code, right? So you like C Codegen. This isn't used. Codegen / though. We can probably start finding some like ZCU maybe sounds kind of interesting. It's like some letters that I don't know. Zig compilation unit. Yeah, okay. So they have like AIR in here, and they probably turned this into LLVM objects or something. Probably would be my guess here. Looks like the LLVM stuff is owned by ZCU, which is us. Oh, sure. This is like self here. AIR. Where is this used in here? he not doing a lot here. He's just checking that these fields are all the same. Okay, so maybe it's not here. x86-64 Codegen. Yeah, it might be worth looking there, huh? Like, who calls this stuff is probably interesting, right? So someone somewhere is like spitting out some assembly, right? And that's gotta somehow tie back. Generate. Taking in per thread data for the compilation unit. Taking in the analyzed IR. Okay. And then presumably emits MIR. This is probably maybe this is like write instruction. So probably they have some sort of like emit here is probably some type that's like fed in or like configured to output something specific. Oh, this is ARM. Wait, hold on. x86 emit. Okay, so this is where the actual assembly is generated, would I guess, right? So we kind of understand, I guess it's like we have AST, I think the flow is, if I understand correctly, Zig compiler. It's like AST, so it's like source code to AST to ZIR to AIR with two like code gen in x86-64 to emit. Something like this. And so, you know, I guess probably we can like looking at like these layers is probably good enough for us. Probably even this layer maybe is good enough for us to understand how, like, what it's expecting to try to do with errors at least a little bit. So can we go back to like, I wonder if we like just search for like error in here, or like is error like, we looking like in here, is it like error? No. Would have been too nice. But if we look for like error in here, I wonder if that's interesting in some way. There's like error value stuff in here. What is going on here? I see. Okay. Error value. Is someone doing something like this with this? In here, if they see an error value, they do something here when they're converting to AIR. So they go, we saw some error value thing. Create an error set with this type. Sure. And then this creates some sort of like error type in AIR. Confusing. Okay. I'm a little lost, which is fine. You know, it is what it is. But maybe we can take a look at the disassembly a little bit on the other side, try to get a feel from there, because I think that it's going to take me a while to tie this back from this side. This feels like it's going to get complicated. Yeah, so let's maybe like run this thing in our crash case. And can we look at like exactly what it's trying to do on like frame 2 here? So just kind of like at like a machine level, he's trying to store R0, R1, R2. What does this mean? Let's look up this instruction. Maybe this is the way Instruction set. Here we go. Oops. Probably the ARM reference manual is like a little bit of a better place to look for this, but if he just tells me, yeah, let's look at the ARM reference manual maybe. And is there like a list of instructions here? Can we just look for like str here? Load and store. Here we go. Is there like a fucking link to somewhere? A4 summarizes the general purpose register. See also this. Load and store multiple. I'm more interested in like what store can do, no? Does this not give me, what is like A4? About the instruction instead. Load and store instructions. Okay, but like, see addressing modes for more. Addressing modes for load and store is formed for two parts, a value from a base register and an offset. Okay. Base register is one of these. For loads, the base register can be the program counter, blah, blah, blah. Takes one of two formats. Immediate. Offset is an unsigned number that can be added to or subtracted from the base register value. Register. Offset is a value from a general purpose register. Oh, so I guess they're saying like take the offset from R2 of R1 and store that in R0 or something. Right? That's probably what this is. Where R1 and R2 at this point are like absolutely fucked. But I guess maybe these registers are not like in the state that they would be here. Right, I guess. So can we breakpoint here and rerun? We have to be careful because we kind of have to like, we have to, the way breakpoints work is they like replace instructions with a breakpoint instruction, but our bootloader copies the entire program into memory, which would overwrite setting a breakpoint on rerun. So what we should do is we should breakpoint here at the beginning of main, then set our breakpoint at this spot. Oh, but that's the wrong address now? Fuck. Probably. So maybe we can just run, we can just continue, I guess. See where this thing is, which is here still. So we can breakpoint, we can run again, breakpoint at this address, continue. And where are we here? Are we in the right thing? We are. Okay, so theoretically we're at the exact instruction that causes a problem, right? So if I info registers, he's trying to store this stuff, which are kind of like mega big values, okay? Then we go next instruction. Boom, we hit our hard fault. Okay, so that's good. That's good. So now we can, oopsies, I shouldn't have done that. Okay, so breakpoint, fuck, what was it? Run breakpoint at here. Info registers. Okay, so here. Oh, oops. Continue. Info registers. All right, here we go. So these are the values in R1 and R2, which are like, seem pretty fucked to me, right? If we're saying like, store here, this was this, it's like, what the fuck are we doing, right? This seem like, these don't seem like sane numbers. These aren't even like in RAM, right? Like our RAM on this chip is something like, I think it's in the range of like hex 2 whatever a bunch of zeros to like 2004 a bunch of zeros, right? Like something in that range. Not like this. These are like not values that we could write to in memory, right? So it makes sense that we would hard fault there, right? In fact, I bet you we could trigger a hard fault if we're just like, const x is a, some like u32 pointer from int of this, right? And we try to do like x dot star. I bet you this should just like immediately hard fault, right? Sorry, 1 second. Continue. Right. So here we've got the same thing, right? We're just like going to some fucking random fucking address, slapping that shit in there, and he's getting mad, right? So I guess now the question becomes, where is that coming from? Right? So it was like continue, backtrace, breakpoint here. Run, del1, breakpoint here, breakpoint here, del2, continue. Okay. So we're in built-in.zig. Can we like look at this function? So we're like calling error return trace, which is scary, right? That's fucking scary. Right? I don't think that we should be storing anything at 0. I'll throw that out there. Then we are trying to assign to this guy. We are trying to assign to this guy this thing, which I also don't know what like return address is. I wonder if we can okay, so this is coming from do a thing. Then he's immediately ending up at built-in return error. And it's hard to think, like, I don't know if it's like valid for us to just call this function. Okay. Disassemble this whole thing. Maybe we can try to like piece it together. Right? This whole function, there's not a lot going on here, right? So sub stack pointer, move R1 to the link at register. Okay. Store. Oh, which way does this go? Is this the stored value or is this the stored value? I don't really know which way this goes. It must be this way, right? He's taking R1 and he's putting it in here, here, right? It has to be. It has to be that way. Right? Because there's no point in loading from the stack pointer into R1 3 times. Right? So, yeah, that's what this guy's saying. Store RT, RN number offset. RT is the stored value. RN is the base register containing the address. Sure. So here, we're trying to store the value of R0 into that shit. Sure. We put so much stuff in the stack. Then, I assume this just goes the other way, right? He's taking... loading R1 plus some amount into here, and then loading the second value into here, comparing them, right? So that compare is got to be, oopsies. How do I like list GDB reset list? Command. No, GDB list. However, if the last line printed was a solitary line, printed as part of displaying a stack frame. Sure, so we're just like frame, list. There we go. So this comparison here is probably this. Sorry, this. And if it jumps to like either here or just goes straight to the end, sure, which is here. Yeah. Okay. So then that's kind of like all of... Oh, and then this goes back to plus 24. So this is kind of like the final. This is the end, the very end. So he like resets the stack pointer. He adds 1 to R0, and then he puts the result back in st.index, right? So that means that st is probably the thing in R1, right? That kind of lines up, right? So here, when he's doing store this thing, R0 is the return address, probably. R1 is st, and R2 is like this shit, probably. Right? That seems reasonable. So this is just fucked, right? Like, I think the problem here is that st is just like garbage, right? The return trace, the error return trace, is just pulling from somewhere, right? And it's just like garbage. That seems like the problem. So I guess the question becomes, where the fuck does error return trace come from? Maybe the language reference will help us out a little bit here. I'm curious, just at least a little bit. Error. Maybe we can read the part of this thing about errors in general. Like, surely there's like a section on this thing in errors. Let's get what the documentation of the language says these things should be. So we got like an error is like an enum. However, each error name gets assigned a unsigned integer greater than 0. You're allowed to declare the same error name more than once. But it might get the same integer value. Sure. You can do some coercion. None of this is really matter. The global error set is, his own thing. Error union type. This is not really that interesting. I'm more interested in like the backtracing stuff. Okay, this is talking about how to use them with tries and catches. More kind of like language level shit. Merging error sets, inferred error sets. None of this is really... Okay, they talk about the return traces are enabled by default, debug release safe, and disabled by default here. This is kind of more where I'm interested. Error return traces show all the points in your code that an error was returned at the calling function. Yes. Okay. Sure. Use error return trace, blah, blah, blah. Okay. Implementation details. Here we go. This is what I'm looking for. When no errors return and when returning errors, things are different. Is there some Zig runtime environment set we should have done boot to? That's kind of what I'm assuming, right? That's what I'm assuming. For this case, when no errors return, the cost is a single memory write operation. Only in the first non-available function call in the call graph that calls available function. This is to initialize this struct in the stacked memory. Oh. Okay. So that's kind of claiming that, like, here, when he calls main, because main is a available function, that, like, the stack trace gets set. Okay. A pointer to stack trace is passed as a secret parameter to every function that can return an error, but it is always the first parameter. So it can likely sit in a register and stay there. Oh, okay, wait, hold on. So in an interrupt handler, my stack pointer is different. Okay? So that's it for the path where no errors occur. Sure. So they like put the thing in there. Then when it does return, he generates what is essentially this thing, which is basically what we're looking at, right? So really, he's saying that like as a secret parameter to every function that might return error. So probably like SVC handler, when we call do a thing, we have to set the register for the return for like the stack return stack. Okay, so let's look at where is our stack in the context of interrupts, because we intentionally set it to be something else. Interrupt here. So here interrupt stack comes here, and so we should start here and kind of like move downwards, right? So that's kind of the intent here. Oh fuck, and our interrupt stack is short. I think our interrupt stack might be like 256 bytes. It might be fucked. So when we like first get called, we make room for a 1K stack at the end of RAM for interrupts. And then we start the rest of our stack below that. Okay, 1K. So we have 1K, and it's possible that that's not enough, right? That's something that we should keep an eye on. So when we call our SVC handler, we slap a breakpoint here, okay? And, oh wait, what the fuck was that? Wait, hold on. I saw an error somewhere that I didn't like. Crash me. Sure, whatever. That's fine. Doesn't matter. Does not matter. Okay. So if we print the stack pointer now, our info registers. Oops, this is not the right one. Okay, info registers when we start interrupt handler. We should have our stack pointer is basically at 40000. It's off by a little bit, which is interesting. But it's because we've already done all of this stuff by the time we hit our breakpoint, right? So here we've added 8 to our stack pointer. Is that it? Then we've put, hold on, what am I looking at here? What am I looking at here? So our stack pointer is here. So can we do like 0x20400000 minus this? How far have we moved? Holy fuck. I mean, we're definitely out of valid memory. That's a big number. How did we end up like this? Like, am I crazy that like this interrupt stack is supposed to be here, right? So can we, okay, let's not call do a thing and run this again. Stack pointer, this is way closer, right? So 0x20040000 minus this. Even that's really fucking big. This is also a good clue, that 800. We definitely saw 800 before. So my understanding was that at this point, our stack pointer is supposed to be whatever we set here. So that's kind of odd. That doesn't seem right at all. Unless the stack... No, it doesn't make sense. Very interesting. Very, very interesting. Disassemble. Yeah, it's like nothing. This function's doing jack shit. Like literally like nothing. So why is our stack pointer so large? Can we go back to frame? Can we just hit continue here a little bit? Okay, let's go to functions.s and add a breakpoint after this. So after this guy's called, let's see if we're like, if for some reason the stack switch isn't happening. Okay. Info registers in our normal context right after calling that thing. I should have written it down both times. Hold on. Okay. So we get into our signal handler. This is our stack pointer. Okay? FAFO. FAFO. Is there a reason why I use SVC0 at Crashman instead of UDF? Just because, like, I don't know, it's the first thing I found. Is hardware pushing a bunch of state automatically when the interrupt gets fired? Still one case seems excessive. Yeah, that does sound familiar, actually. So in our normal context, we're here, B10, and then in our interrupt handler, we're at FAFO, right? So this number is smaller than this number, which is concerning, right? That's like pretty fucking concerning. Because that means that, like, if the stack grows down, which I'm pretty fucking sure it does, then that means that, like, it feels like we're not doing the stack switch. That's how it feels to me. Which is like, the fuck? Yeah, that seems fucked. So, also, what's like 1K mine? Like 0x2004 minus 1024. 3FC, right? So our normal stack outside of interrupt handlers starts here and grows down. So it's like both of these numbers are lower than that. Right, FAFO, that's lower. FB1, right? So if we go like this minus the stack at crash me. Yeah, okay. It feels to me like the stack switch isn't happening. That's what it feels like to me. Which would explain a lot. So we have our interrupt table as like a thing in global memory. Can we breakpoint here and just kind of look at the interrupt table? Like something feels fishy to me. I guess... Can I look at this maybe? Const x is equal to, you know, this. And then this. All right. So this is where the interrupt table lives. kind of low in our total memory space, close to 2000 whole. So if we look at the thing here, the first thing we see is correct, right? This is the value that we're looking for. But it'd be interesting to like continue on here and look at this thing again, right? So when we enter the interrupt handler, that is still correct. Okay, so that's interesting. Okay, so I wonder if we've missed something there. In like, so I think it was in here where they talk about stack alignment on exception entry, maybe. Stack pointer to be an 8-byte aligned address because exception handlers are normally written, blah, blah, blah. Accepted entry behavior, right. Okay, so on preemption of the instruction stream, the hardware saves the context state onto a stack pointed to by one of the SP registers. Whoa. The fuck? Maybe this is what I was confused. Main stack pointer and process stack pointer. PSP. The current stack depends on the mode, and in thread mode. Okay, sure. So let's maybe take a little bit of a closer look at that. So we have MSP and PSP. We're certainly in MSP, right? PSP is like just fucked. Okay, so cool. The stack used depends on the mode of processor at the time of exception. Sure. Stacked context supports this. This means the exception handler can be this compliant procedure. Use a full descending stack where, when pushing context, hardware decrements the stack pointer, right? When popping, blah, blah, blah. When pushing context to the stack, hardware saves these guys. And this describes the behavior. So on entry, they push to the current stack. Then they push the exception type. Okay. Which does all of this stuff. Sure. Then, am I crazy that it doesn't look like they're using that? Like, I don't see anything that says we switch the stack. So why did I think that? Why did I think that? Because when we looked at like the interrupt table, where was that? That was programmer's model, exceptions, faults, and interrupts. No. Where was that table here? Yeah, I don't know why I thought that. There's IPSR update in exception taken. ISPR being the instruction type. Oh. Okay, let me look at that again. You're saying that you have ISPR somewhere in here. Or IPSR? Update? Oh, here, yeah, okay. So on exception taken, which is the second part, update IPSR to this I see. Current stack is now SP main. Okay, can we look up IPSR? Maybe that's... Processor updates IPSR on entry and exit. Software can run this to read that thing. In handler mode, the exception number is this guy. Okay. Can we look at like the interrupt vector table? Like exception table maybe? Vector table here. This is the reset value. Yeah, okay, so this is where we got that from, right? We said the 0th thing is the reset value of the main stack pointer. On reset. Maybe this is not reset. So reset is only one of the exceptions. So maybe they're just sharing the default stack normally? Which is like maybe fine? Maybe? Is used to initialize the value for SP main, all entries. Yeah, maybe I misunderstood that. SVC might be special as well. Yeah, that's a good point. I could get behind that. We can check that by going into init USB, looking at the USB interrupt handler, right? We can compare here. Okay. Info registers. Yeah. Interesting. Good eye. So SVC might be special, right? Because here the stack switch is definitely happening. Okay. Good eye. So let's kind of work in this context then. That makes more sense. Does that mean the common stocks for all handlers? I think that it might actually just be that SVC is special. Because here in the USB interrupt handler, we're definitely changing stacks. So there's something that I'm not like fully grokking there. But fuck it. So here, this should fail, is our understanding right now. So we get into the USB interrupt handler. Oh, wait, hold on. Are we okay now? Whoa. That's confusing. So it worked once? And then failed the second time? Is that what we fucking saw here? Zig build. So we hit one breakpoint in USB RQ, which means we made it through the function. We run again. And it crashes. So I guess this could be, it's hard to know if this is after the interrupt, if this is like cleanup code, or if we made it out. Yeah, so we did make it back out of the section, and then on the second interrupt, we're still chilling. Third, fourth. Okay, now we break. So it's not consistent, which is also interesting. The donkey said to me that all interrupts get the switch, and that would make sense. Yeah, I mean, that is, it's maybe just SVC is special. So I'm not going to worry too much about it. Not going to worry too much about it. So we are in a state now where our stack pointer is close to the end. Great. I would love to maybe can we just run this and see, watch it fail? Okay. So we have failed. And can we go backtrace a little bit? Frame 4 maybe, frame 2, info registers. So it would make sense here if we're trying to access near 0, that would be a problem. It's just such like an unclear error. So again, we comment this stuff out. We shouldn't be failing anymore, right? Now he's just probably happy. Yeah, no crashy, right? Everything's making sense. I would be interested in maybe using rint to enum and converting it back to returning an error. This will let us like annotate this a little better. Okay. So here we're hoping to see the same problem occur, which we are. And can we maybe like is this the problem here? Is it here we're failing? I think it is. Okay. So we hit continue. No, maybe not. Okay. Breakpoint here or here. Maybe down here. Okay. Okay. So now we can look at exactly what's happening. So this is the next instruction a few times. We return uh-oh. Return error uh-oh. Then are we just kind of like fine? What's happening? Okay, so we're kind of moving through this. Oh, then we're chilling. Okay, so we go again. We hit next instruction a few times. Hit continue again. That's really interesting. So it's like the third run of this thing is like causing the problem. Maybe what we should do is log the registers on entry. Or can we see if like if we put a breakpoint here, how does that kind of play out? So we run this guy. We hit the first breakpoint once, then the one in int enum, so that's 1, 2. Then the second interrupt. Oh, then we crash before hitting either one again. Okay. So is it like on exit? Is it like... Let's look a little closer. Continue, continue, continue. Crashy, crashy. Right, so at frame 2, disassemble. We're at offset 10. Nobody's branching back to offset 10. Right, so it seems like this is actually on entry to the function. And they're loading register 0. They're giving him the value of R1, the pointer in R1. So the pointer in R1, garbage, right? 9. Why? He moved R0 into R1 here. So he's just kind of using R0 raw here at the beginning of the function. That seems kind of wrong. Right? Why would he assume here that R0 is like known? That's weird. This is probably the bug. Right? Because then all the rest of these guys... Oh, no, wait, hold on. No, my bad. I don't know what the fuck this is for. But here he's taking the value of the stack pointer, offset by 8, and storing that in R1. Okay. So stack pointer here is this. So wait, why was R1 9 then? I'm confused in a lot of ways here. So this is taking... Isn't he taking R1 and putting a stack pointer plus... Oh yeah, sorry, my bad. You're right. So if we take the value of stack pointer, plus 8, and we dereference him, we're expecting to see a 9? Yes. You are right. So he takes R1, he puts in the stack pointer. So the fact that R1 and R0 here are set at, or like being used raw seems fucking crazy to me. Right? That's weird. Especially since our function takes no arguments. So I guess it's that he's expecting R0 to have... What is like ARM calling convention? Hold on. It's supposed to have the special stack trace thingy, but I thought that was only on functions that returned errors. I thought that they said that the first function that calls an error is a function that returns an error is the one that propagates that thing, right? So like USB IRQ does not return an error. So why would that be passed through? You know what I mean? You know, but maybe I misunderstood. Argument values are supposed to be R0 to R3, right? That's kind of my understanding. But maybe what you guys are saying is true, right? Maybe it's actually like, how do I say this? Maybe it's like the fact that main returns an error means that R0, like all Zig functions from main down have this like shit injected. Only in the first non-failable function in the call graph that calls a failable function, i.e. when a function returning void calls a function returning error. See, this is the case that I think we should be in. So that just makes this feel really strange. I'm curious if we can like manipulate this somehow into happening outside the context of an interrupt. Cause like, okay, can we actually, I just want to confirm here. Let's breakpoint on this address. Run, breakpoint here. I want to make sure that I understand the order of operations here. So if we have here, R0 is 0, R1 is 0. So that's not helpful. But if I say like, can I set a register here? GDB set register. Modify GDB modify register. Is that like allowed? No, I don't want to like do modifying registers. Here we go. Set. Okay, sure. So we're like set R So if I think I'm pretty sure it's moving R0 into R1 here. So we say set R0 equals 0x1. Okay, and then we next instruction. Hello? Next instruction. Yeah, okay. Yeah, so he's taking R0 moving to R1. So the only assumption here at the beginning is that R0 has something, but I guess then he's just, maybe then he's just preserving, he's preserving R1, the old value of R0, he's preserving. That's essentially what this is doing, right? He's saying like, take the thing that was in R0, put him somewhere for safekeeping. Maybe is what he's saying here. Then he's like, load the thing that was in R0 before and like dereference that guy. And then store the dereference thing in the stack pointer. And this is what's failing because like R0 was not a valid thing. Okay. So it really does seem like confusing. Because I just don't really understand why he would assume R0 is valid here. It just seems fucking crazy. What if we do like X, like, can we do like call conf C here? Where does this go? Like this? I wonder if that changes shit. Okay. So now, what does this look like? Now he's like, definitely, it's definitely different. Definitely different. And now the error doesn't occur anymore? Right, so that kind of lines up with the idea that Zig is expecting that the like stack trace value is being passed down. And I guess it could be that like in the backtrace here, main is a function that returns an error, right? So theoretically, it could be using that information somehow. Somehow, but no, because USB IRQ here is unfucking conditionally doing that, right? He doesn't know necessarily who he's called by, I don't think, unless they're assuming that everyone is called by main. So they could be saying something like, if main returns an error, every function that we can like tie back in that call graph also is like holding that error backtrace. That's possible. That's possible, right? So maybe if we do something like function main here, let's make him not return an error. And let's see if that changes the behavior. Okay. So continue, disassemble. This looks the same, right? Like he's still just using R0 raw. So we should see the failure happen again here, yes. So this just doesn't line up with what they're saying. Can we look at like maybe, I want to look at something that's like less sketchy. Let's look at do a thing. I would think that every function on the way that can return an error must have a stack trace. No? Otherwise it'd be cut out. Maybe I'm missing something. So my understanding is that like every time a function that doesn't return an error returns an error. So you have like A returns void. Calls B returns, error void. My understanding that is that every time we have this transition, we should be allocating some space on the stack for the return trace, right? And passing this address as RZ as the first argument to this function. And so like my understanding is that you could have like 4 stacks. You could have like many return trace stacks. Right, if you have like a chain of like A calls B, calls A, calls B, calls A, calls B, right, you would have like one trace here, and then this one could generate like a new trace, and then a new trace, because these traces aren't like linked together, if that makes sense. Like in terms of like the error. Yeah, there's something there where like I would expect a new trace to be generated for each of these, not like a shared one. But maybe I'm wrong. I wonder if it's like maybe just every function in Zig is like expecting this shit. I wonder if every function in Zig in debug mode is just using R0 as the error return trace and doing something. Let's read the language reference a little more. So here we are saying that we have some thing in here that has n slots for instruction addresses. Here, n is the maximum function call depth as determined by call graph analysis. Okay. A pointer to a stack trace is passed as a secret parameter to every function that can return an error, but it's always the first parameter, so it can likely sit in a register and stay there. So I wonder if R0 is just always holding this thing on every function call. Could be. Could be. So I want to look at like maybe do a thing. Can we look breakpoint? Okay. Let's see what do a thing looks like. So here, he's like move 1 into R0, which is like a failure. Because R0 is the return value, sure. And then I guess probably here he's branching to return error, who is probably looking at R0 directly here. So here, R0 probably has like a valid point in the stack where this like stack trace should be written. Okay, that makes sense to me. Right, so like before we call do a thing in main here, my understanding is that we should be making some space. Yeah, right, they load some space for this guy, right? They go put stack pointer. Oh, here, okay. Okay. I mean, this is a pretty fucking good indication that that's the case, right? So they have the thing that they're the stack trace thing is at stack pointer 28 here, and they're literally putting it in R0 before every single function call in main. Right? So despite the fact that main does not return an error, and none of these functions that he's calling return an error, he's still fucking doing it. Didn't the doc say that the first time that the transition happens, the thing is allocated, and making every function required to know if they're before or after that first time is unreasonable, so they just all assume they need to preserve the register? That sounds reasonable to me. It's not crazy, right? So I guess that means that this USB IRQ function is assuming on entry that R0 is the pointer to that stack trace guy. And so the correct answer here is that all of our IRQs just should be call conv C. I think that that's the correct answer here. I think. Init interrupt table, which means that like we should probably do something more intelligent here and do like assign interrupt table function. And in here, we should take like a pointer to, you know, call conv C, you know, something like this. I don't know if this is the right thing, right? And then here we go, interrupt vector table index is equal to F. Yeah. Or conv naked. I think we don't want conv naked because we do want him to preserve like the way that the interrupt handler preserves registers. It preserves all the registers that a normal function with the C calling convention would expect to be preserved and doesn't preserve the rest. So like the like internal backing up mechanism, we kind of want it to be what it would be on a default C calling convention. I think. And so now all of these we can be like assign interrupt table function to do nothing, right? And he should be mad that the types don't match anymore. So this can be const. And then this guy should be like call conv C. Cool. And so now we just do that for all of these. And the type system should get mad at us now. Yes. Okay. So here, we need to replace all of these voids with call conv C void. Okay. All right. Cool. And then all of these guys we need to replace. So it's assign interrupt table function. Find this. I think I fucked up the macro. Assign interrupt table function. Find this. Delete, find this. And then go again. Nice. Okay, there we go. Cool. And then we just have to fix this on all of them. All right. Hype. And so now we should be able to go back to... Oh, I guess we should do this in main, not in our little test thing. God damn it. So can we go back to the normal USB IRQ? Init interrupt vector table here. We create this function. We run our macro. Yup. And then we have to apply those fixes here as well. Oops. Okay. Boom. Oops. Boom. 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 Okay. And then in our build.zig, let's go back to main. In here, we'll go back to in int to enum. We replace this with stud meta now, and we can put a catch in here now. Everybody should be happy. Okay. And let's see if everything works now. So what are we expecting to see here? What are we expecting to see here? We're expecting to see no crashes, I guess. And we're expecting to see an LS USB, because that's what this thing is supposed to be doing. It's supposed to be initializing himself as a USB device. We should see Spheriforia's controller here. No crashy. Maybe? Fuck yes, dude. Okay, I wonder if that fixed some of the other kind of weird behaviors we were seeing yesterday, where we were getting like kind of really inconsistent failures in the USB interrupt handling stuff. We had like string stuff where if we kind of modified our, manufacturer string to like Spherifria, manufacturer and like controller for children, we start to see like kind of pretty aggressive crashes here. And I wonder if that's the reason. Oh, it is sick, dude. So yesterday I was like, is there like alignment problems with this thing? But I guess it's just that R0 was like making it through places and getting dereferenced, and just depending on what was on the stack, sometimes it would just like fuck shit up. That's so interesting. Okay, so that's like an interesting piece of info that's like good to have in the brain for forever. Is like Zig will just eat a register argument for all functions forever, and that's like really important for stuff like this. So probably the rule of thumb should be that if you're ever interacting with like an external system, you should be using like intentional calling conventions, right? I was kind of letting it go because I was like, the Zig calling convention seems to be fine. Fuck it, whatever. But yeah, that was stupid. I shouldn't just be using Zig function pointers, because Zig is assuming when it's working with itself that it can follow its own rules that are maybe different than the rules that an external system would follow. And of course, any, I think, competent low-level programmer would have just assumed that to begin with. Like, it's kind of silly for me to have ever thought that this would work. And I guess I was this is like the classic, you're working in C, C++, and you develop by experimentation, and then like 6 months later something bites you. This is the fucking classic, right? You think that just because something worked, that meant it's okay, and that's not how things work. You have to be careful about like the expectations of these things, because a small misunderstanding like that can cause like pretty big problems down the road. It was working though until it did not. Yeah, exactly. This is how that type of shit happens. So cool. I think that was a successful investigation. I guess we call it there. Thanks for watching, guys. If you like what you saw, we stream most days at 12:30. It is 2:30 now, right? So 2 hours ago, we try to go for, this is a really, really short stream. Typically we try to go longer, but I didn't really have much of a backup plan. Yeah, if you want to support the stream, sometimes we do 2 portions of the stream. Like today, actually, we did kind of like a half-hour initial make a stripped down test case type of thing. We do sometimes these like background work, prep work, refactoring, testing, reading, all that type of stuff. That goes in this like second segment of the stream we call Happy Hour. And if you want to support the stream, you can support on Patreon, YouTube, or Twitch, and you get access to those components of VODs. You can, of course, catch them live for free, but if you miss them live, that's how you get them. The stream will die someday, so and that day is like when I run out of money, right? So every dollar I make does extend the lifetime of this by some amount. So appreciate it. Yeah. YouTube, peace out, and Twitch is fun someone to raid.